They've been lying to you without even realizing it. You've heard it in classrooms, documentaries, science fiction films, even the news. That star is a million light years away, and every time there's the same quiet implication that this is about time. That light years measure age, but they don't. A light year doesn't measure time. A light year measures distance. And it's one of the most profoundly misunderstood concepts in all of science. Let's break it open. The term light year was first coined in the 19th century, and it sounds innocent enough. The distance light travels in 1 year. But that word, year, is what traps people. We think in time, and so, instinctively, we assign a temporal meaning to a spatial unit. But here's the reality. A light year is a measurement of how far light can travel through the vacuum of space in the span of 1 Earth year. That number? 9.46 trillion kilometers. 9,460 billion kilometers. In just 1 year. That's how fast light is. And that's how staggeringly vast space is. Now here's where it gets dangerous, because most people conflate light year with years ago. They hear, this galaxy is 1 billion light years away, and think, oh, that means it's a billion years old. Or, we're seeing it as it looked a billion years ago. And while that second statement is technically true, it's a dangerous half-truth. Because in science, precision is survival. Let's be precise. A light year tells us how far the light has traveled from a source to us. That's a distance. But because the speed of light is constant and finite, the farther away something is, the older the light we're seeing. So yes, seeing something a billion light years away means we're seeing it as it looked a billion years ago. But that's not what a light year measures. That's a byproduct, a consequence, not the unit itself. And yet, this misunderstanding permeates everything. Textbooks misuse it. Teachers gloss over it. Even some documentaries fail to clarify the distinction. It's not entirely their fault. This is a failure of science communication, and it's persisted for decades. The unit sounds deceptively intuitive, but it's fundamentally alien to human experience. We don't measure distances in how long it takes something to travel them. That would be like measuring a road trip in car hours. You don't say Los Angeles is 5 car hours from San Francisco. That's absurd. But with light years, that's exactly what we're doing. And here's the twisted truth. The reason we even have to use a unit like this is because normal numbers just don't work anymore. Space is too big. It breaks kilometers. It breaks miles. It breaks anything that resembles human scale. So we had to invent a unit that uses light, the fastest thing in the universe, as our measuring stick. And even that feels too slow. And the speed of light? 299,792 kilometers per second. That's roughly 186,000 miles per second. Not per hour, per second. Light circles Earth more than 7 times in a single second. It travels from the Moon to the Earth in just over 1 second. It reaches from the Sun to the Earth in about 8 minutes. And even that is nothing compared to the sheer distances we're about to face. But before we go there, ask yourself, why don't we just use kilometers? Why not stick to meters, or parsecs, or astronomical units? Because the truth is, space outgrew those measurements long ago. Astronomical units work fine for within our solar system. They're based on the average distance between the Earth and the Sun, about 150 million kilometers. But once you step outside the solar system, even the AU becomes useless. The nearest star, Proxima Centauri, is over 268,000 AU away. No one wants to work with numbers that big, that clumsy, that messy. We need something cleaner, something built for this scale. Enter the light year. And yet, despite being such a critical tool, it remains misunderstood, used casually, and interpreted sloppily. If you think this is just semantics, think again, because misunderstanding the light year has consequences. It leads people to misjudge the age of stars, the structure of galaxies, the very shape of the universe itself. It blurs the boundary between what's far and what's old. It warps our understanding of space, time, and motion. It creates false impressions and false confidence. And here's the uncomfortable reality. Even scientists occasionally get sloppy. They throw around light years, assuming everyone in the room understands. But they don't. Most people don't. And no one wants to admit it. So let's fix it. A light year is the distance light travels in a vacuum in 1 Earth year. That's all. It's a measure of space, not time. But because light takes time to travel across space, we end up seeing things as they were in the past. This misunderstanding exists because the universe itself behaves in a way that tricks our perception. We are bound by light speed, and that boundary is deceptive. It creates a cosmos where every direction we look is the past. Every star, every galaxy, every flash of light, it's already over. What we're seeing has already happened. The universe is not a place, it's a memory. And if that doesn't disturb you yet, just wait. Because in the next section, we're going to show you just how far a light year really is, and how utterly terrifying that distance becomes when you try to cross it. Let's get one thing absolutely clear. When we say a light year is 9.46 trillion kilometers, we're not describing something big. We're describing something monstrous, something that shatters scale, something so incomprehensibly massive that even the word distance starts to feel like a lie. So let's break it down. Let's get uncomfortable. Start with something familiar, a commercial jetliner. A Boeing 747 cruises at around 900 kilometers per hour. That's fast for humans, faster than sound. Now imagine you could board that plane with an endless fuel supply and no need to land. You're flying non-stop. How long would it take you to travel just 1 light year? Answer: 1.2 million years. Yes, let that number sit for a second. 1 million years ago, Homo sapiens didn't exist. We weren't even a concept. That's how long you'd be trapped in a metal tube, hurtling through space, just to reach something that's technically still in our local galactic neighborhood. And that's 1 light year. The nearest star system? Over 4. Let's upgrade. Suppose we somehow got our hands on the Parker Solar Probe, the fastest spacecraft humanity has ever built. At its peak, it reaches speeds of about 700,000 kilometers per hour. That's fast enough to travel from New York to Tokyo in under a minute. So surely it could put a dent in a light year, right? Number. Even at that record-breaking speed, the Parker Solar Probe would need over 1,500 years to travel a single light year. That's longer than the Roman Empire existed. It's longer than the entire stretch from the Dark Ages to today. In that time, civilizations rise and fall, languages die, continents change hands, and you still wouldn't have made it out of the solar system's neighborhood. Let's keep going. Let's talk about light itself, the fastest thing in the known universe. 299,792 kilometers per second. That's the cosmic speed limit. And that's not negotiable. According to our best understanding of physics, nothing with mass can reach it. Ever. Even light, with its incredible velocity, takes 8 minutes to get from the Sun to Earth. That's 150 million kilometers, burned through in a flash. But even light takes time. And that's what should terrify you. A single second of light speed travel takes you around Earth 7.5 times. A single minute. Enough to go from Earth to the Moon 20 times. An hour. You've reached the edge of our solar system. But to travel a light year, that's 31.5 million seconds. And light uses every one of them. Blazing through emptiness, through interstellar radiation, through the vacuum between stars. And it still needs a full year to make the trip. This is the scale we're dealing with. This is what 9.46 trillion kilometers really means. It's not just long, it's unforgiving, it's permanent. Try walking it. The average human walks at 5 kilometers per hour. You'd arrive at your destination in about 216 million years. That's right, you could walk for the entire age of the dinosaurs and still not be halfway there. Try driving it. 120 kilometers per hour. Highway speed. You'll get there in just under 90,000 years. What about modern rockets? The Saturn V, the behemoth that launched humans to the moon, could hit speeds around 40,000 kilometers per hour. It would still take over 27,000 years to cross 1 light year. And that's to nowhere. That's just into the void. No planets, no stars, just space, because between us and the next star, there's nothing. Let's talk about Proxima Centauri, the closest star to Earth after the Sun. 4.24 light-years away. That's 40 trillion kilometers. If you could send a spacecraft there, moving at the speed of Voyager 1, our farthest traveling probe so far, it would take over 73,000 years to arrive. And that's to the nearest system, the nearest star. Now try imagining the Milky Way, 100,000 light-years across. 100,000 years for light. Human civilization has existed for less than 1% of that time. Light from the other side of our own galaxy hasn't even reached us since we began writing. The Andromeda Galaxy, 2.5 million light-years away. That means the light we see from it tonight, on a clear sky, began its journey when early humans were learning to use stone tools. Light is showing us a message from a time before history. And it gets worse. The most distant galaxy ever observed by the James Webb Space Telescope is over 13 billion light-years away. That light began traveling when the universe itself was in its infancy, less than 500 million years old. What you see in that distant dot isn't just a galaxy. It's a memory, a relic, a signal from a time so remote that even atoms were still organizing. That's what makes this terrifying, because we're not talking about very far. We're talking about scales that crush language, that bend our understanding of motion, distance, and time. We evolved on a planet where the farthest you could see was the horizon. Now we measure distance in years, because kilometers gave up, because meters surrendered. A light year is 9.46 trillion kilometers. And yet, it's not even far enough. Because even light, as fast as it is too slow. Coming up next, how far can we actually see into space? And why does the answer point to something far more disturbing than mere distance? The distance of a light year is staggering. But understanding just how far we can see, how deep our telescopes have reached, takes that staggering number and weaponizes it. Because we're not just talking about light years anymore, we're talking about billions of them. And with every additional billion, we're not just reaching farther into space, we're falling deeper into time. When you point a telescope at the night sky, you're not seeing stars, you're seeing time. The deeper you look, the further back you go. It's not poetic, it's literal. The light has taken so long to arrive that everything you're seeing no longer exists as you see it. Every photon is a traveler from a dead past, arriving at your eye long after the event it records has vanished. And our telescopes, our most powerful instruments of vision, are time machines. So how far back have we seen? Right now, the deepest image humanity has ever captured comes from the James Webb Space Telescope. That image contains galaxies that are more than 13.4 billion light-years away, which means we're seeing them as they were just 400 million years after the Big Bang. The universe was still a toddler, less than 3% of its current age. There were no solar systems, no planets, no metals, just gas, gravity, and fire. We are staring at the raw scaffolding of reality. That's how far we can see, over 13 billion light-years. But it gets stranger, because the universe has expanded since that light began its journey. So while we see a galaxy at 13 billion light-years, its actual present-day distance from us is even greater, over 30 billion light-years away, thanks to the expansion of space itself. We're not just looking at distant things, we're looking at unreachable ones. They've already moved beyond us. Forever. Now, zoom out. The observable universe, the part we can theoretically see, is about 93 billion light-years in diameter. That number alone is deceptive. It doesn't mean there's a wall at that distance. It just means that beyond that limit, light hasn't had enough time to reach us since the beginning of the universe. We're blind to anything further. Not because it doesn't exist, but because light obeys a speed limit, and the clock has only been ticking for 13.8 billion years. So here's the horror. Everything we know, everything we've ever seen, every galaxy, every cluster, every quasar, every relic of the early cosmos, it's all confined to this 93 billion light-year bubble. But that's just what we can see. The actual universe could be hundreds of times larger, maybe infinite. We don't know. We may never know. Because our vision is capped by physics, there is a hard horizon, a limit to how far we can witness reality. And beyond that limit, silence. But there's more. Because every time we look deeper into space, we're looking closer to the beginning. The cosmic microwave background, the oldest light in the universe, is the ultimate wall. It comes from a time just 380,000 years after the Big Bang. Before that, the universe was too hot for light to travel. Photons were constantly scattered by free electrons. The cosmos was opaque. We call it the surface of last scattering. Beyond it, we can't see. So what lies beyond that wall? We don't know. But that's the terrifying part. Our most advanced tools are pressing against a literal boundary of knowability. We've already mapped all the light that can ever reach us. We've hit the edge of the observable. And what we see there is disturbing. Because the deeper we peer, the more fragile things look. The earliest galaxies are disorganized, chaotic, turbulent, structures barely forming, stars burning furiously and dying quickly. These aren't the majestic spirals and stately ellipses of modern galaxies. These are violent, messy clusters of matter just learning how to exist. We are looking at the origin of complexity, the dawn of structure, the universe forging stars from hydrogen. And it's sobering, because it tells us how far we've come and how much had to go right. But it also reminds us how temporary it all is, because here's the real threat. The farther back we see, the more it seems like we're trapped in a brief golden age. A window in time where stars still shine, galaxies still grow, and physics still permits complexity. But this won't last. The stars are burning through their fuel. Black holes are slowly consuming mass. The expansion of the universe is accelerating, driven by dark energy, a force we still barely understand. And that acceleration is fatal. It means the observable universe is shrinking in practical terms. Not in size, but in reachability. Galaxies that are visible now will one day be invisible. Their light will never reach us again. They'll slip beyond the cosmic event horizon, redshifted into nothingness. 1 trillion years from now, a hypothetical observer in our galaxy would see an empty sky. No galaxies, no background radiation, just darkness. We exist at a moment when the cosmos is still visible, still illuminated. We are seeing the final fireworks before the long, slow fade. And that fading isn't just visual, it's physical. Entropy is marching forward. Black holes will eventually evaporate through Hawking radiation. Stars will go dark. Matter itself may decay. In some models, even protons aren't forever. The universe will become a sparse, cold, featureless void. This isn't science fiction. This is physics. And all of this is revealed through light years. Not just the unit, but the vision they enable. Every observation across billions of light years is a postcard from a dying system. A warning from the past about what the future holds. The universe we know and love, brimming with galaxies, stars, energy, and wonder, is temporary. And it gets worse, because all of this means one thing about us. We are absolutely insignificant. Our entire planet is invisible from even the nearest star. Our radio signals haven't reached 1% of the Milky Way. Our spacecraft have left the solar system, but not even come close to another star. We exist on a blue speck floating inside a solar system, orbiting a star buried in the arm of an average spiral galaxy, one of hundreds of billions. And all of it, is inside the observable universe, the tiny part of space we can actually see. We are a footnote on a footnote inside a footnote. When you look up at the sky and realize that what you're seeing is light that's already dead, that's not awe, that's dread. The universe is not just old, it's ancient, and we are barely here. This is what it means to see across light years, to stare billions of years into the past. We're not just looking at objects, we're looking at the inevitable, at the decay, at the future, written into the bones of the past. And yet, there's an even deeper implication, one that's far more unsettling. If everything we see is delayed by time, if every star, every galaxy, every distant signal is showing us not what is, but what was, then are we ever seeing the present? Are we always living in the past? And what does that mean for how we understand the universe right now? Everything you've ever seen in the night sky is already gone. Not metaphorically, not romantically. Gone, as in, it doesn't exist the way you see it. Because what you're looking at isn't the object. You're looking at a delay, a recording, a cosmic message in a bottle, launched across the void and only now arriving at your eyes. This isn't speculation. This is hard physics. Light takes time to travel, and space is big, unreasonably big. So by the time light from a star or galaxy reaches Earth, the thing that emitted it might have changed or vanished. Let's start close to home. The moon? You see it as it was 1.3 seconds ago. The sun? You're seeing an 8-minute-old version of it. If it disappeared right now, you wouldn't even know until those final photons reached your retinas. That's manageable. But let's push further. The nearest star system, Alpha Centauri, is 4.37 light-years away. That means if it exploded right now, turned into a supernova, it would still shine undisturbed in our sky for over 4 years before we found out. Our most immediate neighbors are ghosts of the recent past. but those are just the local illusions. The real deception begins when we look deep. Sirius, the brightest star in our night sky, is 8.6 light years away. You're seeing it as it looked when Barack Obama was elected president. Betelgeuse? 642 light years. The light hitting your eyes tonight began its journey in the 14th century, while the Black Death was tearing through Europe. The Andromeda Galaxy? You're looking at a 2.5 million year old image. The light left that galaxy when early humans were learning to walk upright. That galaxy may already be colliding with another one, its structure completely altered. But you won't know that until 2.5 million years from now. What you think of as the present is an illusion. We don't observe the universe as it is, we observe it as it was. There is no now in astronomy. Every telescope image is a look into a time capsule. Every distant object is a slice of history. The further away you look, the older the truth becomes. But here's where things break down. Because we tend to believe in simultaneity, that events happen across the universe at the same time, a universal present moment. But Einstein killed that idea over a century ago. There is no universal now. In the theory of relativity, simultaneity depends on your frame of reference. Two events that appear simultaneous from one perspective may occur in completely different orders from another. Time is not absolute. It's not a constant stream shared by all observers. It's fractured, local, and fluid. When you look at a galaxy 10 billion light years away, there is no agreement, anywhere in the universe, about what is happening there now. In other words, we can't know what's happening anywhere but here. Because every signal, every particle of information takes time to arrive. And that time delay isn't fixable. It's not something we can overcome with better sensors or faster telescopes. It's baked into the structure of space-time. And that creates a paradox. We build our understanding of the universe from observations. But every observation is of the past. So what do we really know about the present? Nothing. If a galaxy 12 billion light years away was obliterated by some cosmic event, collision, gamma-ray burst, annihilation, we won't see the evidence until 12 billion years later. It could be gone right now. It could have been gone for longer than Earth has existed, but as far as we know, it still shines. That's not observation. That's a delayed hallucination. The cosmos we see is a fossilized map of a universe that may no longer exist in the form we perceive it. Worse yet, there's no way to verify. We can't send messages. We can't receive real-time updates. We're isolated by light speed delay. This isn't just unsettling. It's epistemological decay. It erodes our very foundation of knowledge. In every other domain of science, you can observe something as it is. In cosmology, you never can. You're always looking at shadows, at echoes, at corpses of ancient light. Now apply that idea to your map of the universe. That bright, elegant structure you see in Hubble Deep Field images, the beautifully arranged clusters, filaments, and cosmic web, it's all gone. Rearranged, collided, consumed. 1 billion years of gravitational evolution has passed since the light left some of those structures. They've interacted with forces and neighbors we'll never witness. The snapshot we see is already outdated by orders of magnitude. We treat them as static features. They're not. They're evolving. We just can't see it in real time. We never will. The result is a disturbing thought. If light is all we have, and light is always late, then our understanding of the universe is a carefully stitched lie. It's useful, yes. It's beautiful, yes. But it's a lie based on lag. Like watching a disaster through a time-locked feed, unable to intervene. unable even to witness it when it happens. This has terrifying consequences for how we model everything. Want to know how galaxies form? You're watching ancient ones that might be representative. Want to measure the age of the universe? You're using radiation frozen in time nearly 14 billion years ago. Want to test dark energy's effect on expansion? You're comparing how galaxies looked billions of years apart, but you're never watching the same galaxy change. We are scientists modeling a machine we can't touch, can't replay, can't fast forward, and can't observe as it operates now. And all of this cascades into one profound implication. We are alone in time. Not just in space, in time. Because even if someone out there sees us, they don't see us now. They see Earth as it was. They don't see you. They see dinosaurs or mammoths or pyramids being built. And if we see them, we're seeing a civilization that may have long since died. Even contact becomes warped. Even communication is delayed beyond usability. The cosmic scale doesn't just separate us by space. It isolates us across time barriers that no technology can break. And yet, we continue to build bigger telescopes. Not to see what is, but to see what was with more clarity. Because it's all we have. That's the paradox. To know the universe is to study its past. But that means we may never truly understand the universe as it is, only what it once was. A record with missing pages, trapped in the infinite delay of light's journey through a relentless void. And if you think that's the end of the story, it's not. Because what happens when we finally realize that we may never go there? That the places we see are so far and our technology so limited that no ship, no probe, no message could ever reach them in time? The next revelation is more crushing than time delay. It's distance itself, because even if we had forever to wait, light years aren't just deceptive in what they show us. They're a wall, a barrier, and crossing even one of them might be physically impossible. Light years are not just measurements. They're not just reminders of distance or warnings of delay. They are prison walls. We imagine interstellar travel as an inevitability. We tell stories of warp drives, hyperspace lanes, wormholes, and quantum jumps. We assume, because we want to, that eventually, somehow, we'll crack the code and slip the leash. That we'll go to the stars, but the numbers say otherwise. The numbers are merciless. Let's start with what we have. Voyager 1, launched in 1977, is the farthest human-made object from Earth. As of now, it's roughly 24 billion kilometers away, still inside the solar system's outer boundary. It's traveling at 61,000 kilometers per hour. Fast by human standards. And yet, if Voyager 1 were aimed at Proxima Centauri, the nearest star system, it would take over 73,000 years to arrive. That's not interstellar travel. That's geological time. That's extinction-level waiting. But what if we used our fastest spacecraft? The Parker Solar Probe, launched in 2018, will eventually reach speeds of about 700,000 kilometers per hour. At that velocity, it would still need around 6,600 years to reach Proxima Centauri. That's 10 times the span of recorded human civilization, just to reach the closest target. This is the cruel math of the cosmos. You can double your speed, triple it, multiply it tenfold. And still, the distances laugh at you, because they're not built for us. They're not made for flesh or metal or fuel. They're measured in the currency of light, something we can't match. Our propulsion systems, chemical rockets, ion thrusters, even theoretical nuclear engines, are hopelessly inadequate. We push against physics with every launch, every engineering marvel, and we barely leave a scratch. The problem isn't just power, it's scale. The energy needed to accelerate even a small craft to a fraction of light speed is astronomical. Want to send a 1-ton probe to just 10% the speed of light? You'd need over 450 trillion joules of energy. That's the total output of the entire world's electrical grid, running at full capacity for months. And that's just to accelerate, not to slow down, not to change direction, just to move. And that's for a probe, not a spacecraft with shielding, life support, redundancy, or crew. Humans make the problem worse. We need radiation protection. We need supplies. We need mass. And the faster you go, the harder space hits back. At relativistic speeds, even a single grain of dust becomes a bullet. The interstellar medium is not empty. It's filled with sparse hydrogen atoms, micrometeorites, and death moving at 1,000 kilometers per second. There is no safe speed, there is no easy path. And the tyranny of the rocket equation makes it worse. To go faster, you need more fuel, but more fuel means more mass. And more mass means you need even more fuel. It's an exponential spiral, a trap that's doomed every ambitious concept we've tried to design. Even theoretical systems, nuclear pulse propulsion, fusion drives, antimatter engines, all face this brutal truth. You can go fast, or you can carry mass, but you can't do both. And if you want to bring humans, you need to do both. There's no shortcut. Not yet. So where does that leave us? Trapped. Trapped inside the solar system. Trapped around one star. Trapped near a pale blue dot orbiting an ordinary sun, while the galaxy stretches out beyond us, taunting. Every time we look up at the stars, we're reminded of the lie. The stars are close in the sky, but unimaginably far in reality. They shine as if inviting us to visit. But every photon that reaches us is another reminder that we're staring across gulfs we cannot cross. And the danger isn't just technological, it's psychological. Because we've grown up with stories of escape, of expansion, of destiny. The idea that humanity will go to the stars isn't just science fiction. It's part of our collective self-image. But what happens if we can't? What happens if we really are trapped here for the next 1,000 years? This isn't speculation. It's where the math points. The challenges of interstellar travel aren't incremental. They're orders of magnitude beyond what we've done. We haven't just failed to leave the solar system. We've barely explored the outer edges of it. We haven't colonized Mars. We haven't even returned to the moon in decades. And while physics doesn't explicitly forbid interstellar travel, it doesn't help either. No law of nature guarantees we'll solve the problem. There is no equation promising warp drives will work. No theorem ensures wormholes are stable. Those ideas, those lifeboats, are just that. Ideas. Theoretical constructs with terrifying uncertainties. We might be stuck. Forever. Because light years don't care about ambition. They don't shrink when you believe harder. They are fixed, immutable, pitiless. And even if we do eventually escape, we will do so at the mercy of time. If it takes thousands of years to reach even the nearest stars, what does that mean for society? For biology? For psychology? Can we build civilizations that persist long enough? Can we protect human minds, human bodies, for millennia in transit? Can a mission launched today survive a 1,000-year voyage? Or would its passengers wake up in a universe that has forgotten them? Worse yet, would they even want to? Because here's the secret no one likes to admit. Distance in space is more than just length. It's isolation. It's disconnection. It's separation from everything you've ever known. Once you leave, you're gone. You're never coming back. This isn't the starship fantasy where people hop between stars like bus stops. This is a one-way trip into oblivion, into silence, into a future that may not remember your name, your culture, your language, or your purpose. The truth is, light years are not units of measurement. They're tombstones. Each one marks a limit to human reach. Each one is a monument to how small we are, how short our lives are, how slow our ships are. Every light year is a wall with no ladder, a moat with no bridge. And unless something fundamental changes, some breakthrough in physics, some leap beyond our current understanding, we will remain trapped in a cosmic prison built not of bars, but of space itself. But even that isn't the whole deception. Because when we say a star is 4 light years away, we're still lying. That number, 4 light years, isn't as fixed as it sounds. Space isn't static. It's expanding, warping, changing. And that means even our simplest statements about the universe are distorted by something far stranger than distance. When someone says, "That star is 4 light years away," it sounds simple, clean, scientific, quantifiable. But that phrase, like much of our language about the universe, is a comforting illusion, because the deeper you look, the more it falls apart. 4 light years. That's supposed to mean light traveling at 299,792 kilometers per second would take 4 Earth years to get from that star to us. And on the surface, that's correct. Except space isn't static, and light doesn't move through a fixed arena. It moves through something that's stretching, warping, shifting beneath it. Space is expanding. This isn't metaphor. This isn't poetic. It's measurable, proven, observed. The universe is getting bigger, and the space between things is growing. Not because galaxies are flying apart through pre-existing space, but because space itself is stretching. So let's break this down. Say you shoot a beam of light from one galaxy to another. As it travels, the very space the light is moving through is expanding. That means the light's wavelength is getting stretched too, literally elongated. This phenomenon is called cosmological redshift, and it breaks everything. Because now, the concept of distance becomes fractured. There's the light travel time distance, how long the light took to reach us. Then there's the moving distance, how far away the object is now, factoring in the expansion that happened during the light's journey. Then there's the angular diameter distance and the luminosity distance. 2 more different values used depending on what you're measuring. So, how far away is that star? It depends. If you say 4 light years away, you're probably referring to light travel time. That's how long ago the light left. But that's not the current distance. Because during those 4 years, the space between Earth and that star has grown. Slightly, for local stars. Mass and gravity keep things tight in our neighborhood, so the effect is minimal, but over large distances, it becomes catastrophic. Let's scale up. Say we're observing a galaxy 13 billion light years away, meaning the light left 13 billion years ago. Due to expansion, that galaxy is now over 30 billion light years away. We will never reach it. Not because of time, not because of speed, but because it's already gone. The space between us and it is expanding faster than light can bridge it. That galaxy, for all practical purposes, has crossed an event horizon. It's in our past, not our space. That's what expansion does. And it gets even more deceptive when we talk about the early universe. Right after the Big Bang, the universe expanded faster than the speed of light. Not because anything violated the laws of physics, but because space itself can expand without limit. This was the era of cosmic inflation, a period when distances between points doubled and doubled again in less than a fraction of a second. It didn't just stretch the universe, it broke our ability to define near and far. Because now, thanks to that inflationary burst, there are parts of the universe far away that light from them has not, and will never, reach us. Not in billions of years. Not ever. They're not just invisible. They are unreachable, cut off by the expansion of space itself. So when someone says, a star is 4 light years away, what does that even mean anymore? If space is expanding, the distance between 2 points depends on when you measure it. It depends on what kind of distance you're using. It depends on what assumptions you're making about the underlying cosmology. And redshift makes it worse. Because we measure distance through redshift, the amount that a galaxy's light has been stretched. But redshift is a proxy, an interpretation. It assumes we know how the universe has expanded over time. If our cosmological model is wrong, even slightly, our measurements are wrong. And it's already happening. There's a tension right now between the observed expansion rate in the early universe, from the cosmic microwave background, and the expansion rate we measure locally, from supernovae and galaxy observations. They don't match. The difference isn't minor. It's statistically significant. Either there's something wrong with our measurements, or something's wrong with our understanding of how space expands. That tension, known as the Hubble tension, points to something deeper. Our grip on distance, speed, and scale is slipping. It means that even our most basic cosmic numbers, like how far away something is, are infected by uncertainty. And there's another layer of deception. Because when we say 4 light years away, we imply that the journey is doable. That if we could just go fast enough, we could get there. But we're ignoring expansion, gravity wells, velocity relative to the cosmic microwave background, and the dynamics of a constantly evolving space-time. Even local travel is subject to relativistic effects. At high speeds, time dilates, distances contract. If you could approach light speed, the star might seem closer from your frame. You'd age slowly. But back on Earth, centuries could pass. The journey becomes a one-way ticket to a future you can never return from. So, what does distance mean in that context? It's not fixed. It's a function of perspective, speed, and cosmic behavior. And that makes 4 light years a dangerous phrase, because it implies a Newtonian, clockwork universe, a reality of rulers and stopwatches. But the universe doesn't care about those tools. It's expanding, warping, moving. It hides its true structure behind relativistic effects and unobservable boundaries. And yet, we keep using that phrase. Because we want to believe we understand. We want the stars to be close. We want the universe to be a place, not a process. But it's not. It's a fluid, shifting arena governed by equations that punish certainty, where distance is only meaningful if you specify the frame, the method, the epoch, the model, which means we've been lying to ourselves every time we imagine the stars as destinations. They're not destinations, they're echoes, moving targets, receding islands in a sea that gets wider every second. And even the closest of them, Alpha Centauri, 4.37 light-years away, feels infinitely farther once you strip away the illusion of a static cosmos. Because between us and them isn't just space. It's time, expansion, distortion, and a billion things we still don't understand. And that deception gets worse when you realize that even that distance, the shortest of all stellar separations, feels impossibly vast. So next, we confront that feeling. The feeling that Alpha Centauri, the nearest star system, might as well be on the other side of the universe. Because what separates us from it is not just kilometers, it's psychological horror. Alpha Centauri is the closest star system to us. At 4.37 light-years away, it's often presented as the first logical destination for humanity's first interstellar journey. It's nearby, within reach, the next-door neighbor in the galactic neighborhood. But that perception of proximity is a cruel misdirection, because Alpha Centauri doesn't feel close, not in any meaningful way. Once you strip away the sterile number, once you start to look at what lies between here and there, it doesn't feel like a neighbor. It feels like a chasm. Let's put it into scale. Start with something familiar, the solar system. From the Sun to Neptune, the most distant planet, is roughly 4.5 billion kilometers. That's about 0.00047 light-years. In cosmic terms, it's microscopic. Voyager 1, humanity's most distant spacecraft, has taken nearly 50 years to reach about 159 astronomical units, or just 0.0025 light-years. That means Voyager 1, moving at over 61,000 kilometers per hour, hasn't even left the cosmic driveway. Now, extend that to Alpha Centauri. To get from our solar system to the closest star system, you'd have to travel over 30,000 times the distance from Earth to the Sun. Not just past the planets, not just past the Kuiper Belt or the Oort cloud, but across an empty, hostile, unforgiving gulf that contains almost nothing. This is the concept of interstellar emptiness. Between stars, the density of matter is staggeringly low, an average of 1 atom per cubic centimeter. That's vacuum. Not the vacuum of a laboratory, not the vacuum of space inside the solar system, but a level of emptiness we are not psychologically built to grasp. Between here and Alpha Centauri, there are no planets, no space stations, no refueling stops, no gravity wells, no familiar signposts, just darkness, radiation, micrometeorites, uncharted cold. And even that doesn't fully communicate it, because the entire solar system, everything you know, everything you've heard of, sits inside a tiny sphere, just 0.001 light-years wide. That's it, from the Sun out to the edge of the Oort cloud, the region dominated by our star's gravity. Once you leave that bubble, you're in true interstellar space, a space so vast that even light needs over 4 years to cross it. And what lies between? Nothing. Not figuratively, literally. Imagine a scale model. If the Sun were the size of a basketball, Earth would be a tiny bead about 25 meters away. Neptune would be over 750 meters out. And Alpha Centauri, it would be over 6,000 kilometers away. That's a planetary scale distance between just 2 stars, in a galaxy filled with hundreds of billions of them. And this distance warps our perception, because we've grown up on maps, on diagrams where planets and stars sit conveniently close for comparison. But those are lies of necessity. They compress vast emptiness into visible inches. In reality, our solar system is an island, a lone archipelago surrounded by an ocean so vast that the nearest shoreline is unreachable with our current ships. Even the concept of sending a signal across that void becomes a test of patience. A radio transmission from Earth would take 4.37 years to arrive. A reply, assuming instant response, would take another 4.37. That's nearly a decade of waiting, just for a greeting and an answer. In the time it takes to say hello and get a hi back, children are born, grow up, and go to school. And the silence? It's relentless, because space between stars doesn't carry sound. There is no wind, no echo, no ambience. A spacecraft traveling through it wouldn't feel like a journey. It would feel like death. No light, no reference points, no acceleration, just the slow, imperceptible drift through a volume of space so immense and so empty that 1,000,000 solar systems could fit inside it without ever noticing each other. This is what makes Alpha Centauri feel farther than it is. Not the light years, not the math, but the psychological horror of distance without context. You can't walk it. You can't see it. You can't feel it passing. You're just there, adrift in the void, crawling forward at a speed that feels like stillness. And if that weren't enough, remember this. Alpha Centauri is actually a binary system. 2 stars orbiting each other, with a possible third, Proxima Centauri, circling farther out. Even when we reach that system, we'll face a chaotic gravitational ballet, a place nothing like Earth, no promise of life, no second home, just another burning ball of fusion surrounded by vacuum. We imagine the stars as stepping stones, but they're not. They're scattered islands, each separated by oceans so vast they defy understanding. And Alpha Centauri? It's the closest island, and still hopelessly out of reach. We're not prepared for that emptiness, because we don't just lack the engines. We lack the imagination, the tools, the psychological resilience to confront what it really means to travel between stars. It's not about bravery, it's about isolation on a cosmic scale. About sending machines or people into journeys where the only thing they'll see for years, decades, centuries is nothing. So when we say Alpha Centauri is only 4.37 light years away, what we should really say is, it might as well be infinity. Because even when we see it, even when we calculate it, even when we name it, the space in between swallows us. And the lie gets worse. Because even the idea of measuring a light year, of defining distance across the cosmos, depends on rules that start to break down once you add gravity, speed, and the curvature of space-time. What you think is far may not be far at all in flat space, but space isn't flat. It's bent, and that changes everything you think you know about distance. The number sounds definitive. 1 light year. The distance light travels in a vacuum in a single Earth year. That's 9.46 trillion kilometers. It's precise, repeatable, universal. But here's the problem. The universe is none of those things, because space isn't flat. It's not uniform. It's not a grid on which light draws straight lines. The moment you add gravity, motion, or scale, that number, 9.46 trillion kilometers, starts to collapse. It becomes meaningless. Or worse, deceptive. We call it the interstellar illusion, the false sense of certainty that comes from treating light years as a reliable measure of distance. And like most illusions, it begins to fall apart under pressure. Start with gravity. Einstein's general relativity changed everything. It taught us that mass bends space, that gravity isn't a force pulling objects together, but the warping of space-time itself. Picture space as a stretched fabric. Place a massive object on it, and the surface curves. Now light, which follows the path of least resistance, no longer moves in a straight line. It follows the curve. This is gravitational lensing, one of the most experimentally verified effects of general relativity. light from a distant star or galaxy bends as it passes near a massive object, like another galaxy or a black hole, creating distorted, magnified, or even multiple images of the same source. So what does that do to distance? Everything. Because if light doesn't travel in a straight line, then the path it takes is longer, or shorter, or more complicated than 9.46 trillion kilometers per year can account for. The distance between 2 points in curved space isn't just about coordinates. It's about geometry. Geometry that shifts depending on where you are, how fast you're moving, and what gravitational fields are nearby. Two observers in different frames of reference might measure the same light's journey and report completely different distances. Which one is right? Both, and neither. Because distance, in curved space, is relative, not just in the Einsteinian sense, but in a fundamental, disturbing way that undermines our entire intuition about space and time. Now add time dilation. As you approach the speed of light, time for you begins to slow, relative to an outside observer. This isn't science fiction. This has been observed with fast-moving particles, with astronauts on the International Space Station, with high-precision atomic clocks flown in jets. But it gets worse, because time also dilates near strong gravitational fields. The closer you are to a massive object, like a black hole, the slower time flows for you as seen by someone farther away. Again, verified, real, not hypothetical. So now imagine sending a spacecraft through curved space near massive stars, around gravity wells, moving at relativistic speeds. What is a light year now? From the spacecraft's point of view, the journey might feel shorter, faster. A light year might be experienced in days. But back on Earth, years have passed, decades, maybe more. The travelers and the observers now disagree, not just on time, but on how far the ship has gone. This isn't just a quirk. It's a systemic breakdown of universal measurement. Because light year assumes a flat, passive backdrop. It assumes light travels at a constant speed, in a constant direction, through a constant medium. None of that is true in general relativity. In real space, warped space, light travels on geodesics, the shortest path through a curved geometry. And those paths are determined by the distribution of mass and energy around them. Light may loop, it may bend, it may get delayed. Yes, delayed. One of the most dramatic examples of this is the Shapiro delay, a relativistic effect where light passing near a massive object takes slightly longer to reach its destination than it would in empty space. Not because the light slows down, but because the curvature of space makes its path longer. Again, measured, verified, used by NASA for deep space communications. So what's the takeaway? The statement, "This galaxy is 2 billion light years away," might mean, "The light took 2 billion years to get here." The galaxy is now much farther than 2 billion light years due to expansion. The light path may have been bent, delayed, or magnified along the way. The actual straight-line distance, if one even exists, is undefined without specifying the geometry of space-time. That's the heart of the illusion. Light years only make sense if space behaves, if it stays still, if it doesn't twist or warp or move. But the universe doesn't behave. It stretches, it flexes, it expands, and it curves in the presence of energy and matter, which means when we draw maps of the cosmos, we are not mapping geography. We're mapping probability distributions, path integrals, relativistic frameworks. Even the best modern tools, like the cosmic distance ladder, depend on a chain of assumptions. Redshifts, standard candles, parallax. Each rung adds uncertainty. Each method depends on the assumption that we understand how light moves through expanding, curving space. And the more distant the object, the more those assumptions break. We might say, this quasar is 13 billion light-years away. But what we mean is, its light has been traveling for 13 billion years through a space-time whose curvature, expansion, and structure we have modeled to the best of our ability. But we can't actually tell you where it is now, or how far away it really is in any absolute sense, because the concept of where it is now might not even be well defined. In curved space, simultaneity breaks down. There may be no objective now that spans both Earth and a galaxy billions of light-years away. Let that sink in. There may be no present moment that both of you share. You can't define its current position, not because of measurement error, but because the fabric of reality doesn't allow you to. So when we teach that a light-year is just distance, we're simplifying a reality that resists simplification. We're trading rigor for comfort, and we get away with it, most of the time. But as we push deeper into space, as we peer further back in time, past billions of light-years of warped and expanding space-time, the illusion becomes lethal to understanding. Our models work because we constrain them. We assume flatness, homogeneity, standard behavior of light. But the universe isn't flat. It's lumpy. Gravitational lensing reveals that dark matter bends space in hidden, unpredictable ways. Time dilation changes the meaning of aging and motion. Cosmic expansion stretches every beam of light beyond what our units were designed to handle. And this isn't theoretical nitpicking. It's foundational. Because if we can't define distance in a way that works across scales, then our cosmological models of dark energy, dark matter, inflation rest on shifting sand. If light years don't tell the whole story, then neither do our maps, our timelines, our histories. They are narratives woven from fragments of ancient light, twisted by gravity, stretched by expansion, and filtered through the curvature of a universe that refuses to stay still. And yet, we cling to the light year, because we need it. We need something to grasp. A way to talk about scale in a cosmos designed to defy scale. But make no mistake, every light year you hear is a simplification, a partial truth, a necessary lie. Because in the real universe, distance is not absolute. It's not even always meaningful. The question isn't just how far. The question is, through what kind of space? And when you finally realize that distance, speed, and time are all distorted by the shape of reality itself, another horrifying truth emerges. Even light, our fastest messenger, is too slow for the universe we've built in our minds. 299,792 kilometers per second. It sounds like the punchline to a superpower, the speed of light, the cosmic speed limit. Nothing, absolutely nothing with mass can go faster. It's the most extreme speed the laws of physics will allow. And yet, in the context of the universe, it's barely fast enough to matter. Because when you're talking about space, you're talking about distances so enormous, so unforgiving, that even light, the fastest thing in the known universe, struggles to keep up. Start small. Earth to the moon. Light makes that trip in just over 1 second. That's fast. So fast it's instant to human perception. A flashlight pointed at the moon reflects back in under 3 seconds. NASA communicates with lunar orbiters in near real time. From Earth to the Sun, 8 minutes and 20 seconds. The light that warms your skin left the sun while you were still scrolling your phone this morning. Already, time is entering the equation. Already, light is not instant. Go farther. Jupiter, about 35 to 52 minutes depending on orbit. Saturn, 70 to 85 minutes. Neptune, over 4 hours, the Voyager. One probe, at the edge of our solar system, receives commands that take over 22 hours to arrive, and another 22 to respond. That's just inside our own star's backyard. Beyond that, light becomes a messenger from history. The nearest star system, Alpha Centauri, is 4.37 light-years away. That's over 4 years of travel time for light. 4 years traveling at 299,792 kilometers every single second, non-stop, without slowing down. And that's the closest other system. From there, the scale explodes. Sirius, the brightest star in our sky, over 8 light-years. Vega, 25. Betelgeuse, roughly 642. And then there's the Andromeda Galaxy, the closest major galaxy to the Milky Way. Light from it takes 2.5 million years to reach us. That's 2.5 million years of uninterrupted travel at maximum speed just to deliver an image. When that light left Andromeda, Homo habilis had just begun using stone tools. The Earth looked nothing like it does today. The light that reaches us now is not just old, it's ancient, it's prehistoric. Andromeda isn't even that far on cosmic scales. It's nearby, a galactic neighbor. The Virgo cluster, a rich collection of galaxies, 55 million light-years. The light we see from those galaxies started its journey when dinosaurs still ruled the Earth. The Coma cluster? 321 million light-years. Quasars, some of the brightest and most energetic objects in the universe, are regularly observed at distances over 12 billion light-years. That means light left those quasars when the universe was just a fraction of its current age, when stars were just beginning to form. That light has been traveling for nearly the entire lifetime of the cosmos, fighting through expanding space, bent by gravity, redshifted by motion, degraded by cosmic dust, and only now, just now, is it arriving. So yes, light is fast, but it is nowhere near fast enough, because while light races forward, the universe continues to stretch. That Andromeda light is 2.5 million years old, but the galaxy it came from? It's now much farther away than that distance implies. The farther you go, the more the destination recedes. The more space expands, the longer the light must run. It's a race that never ends. Take GN-Z11, one of the most distant galaxies ever observed. Its light traveled for 13.4 billion years. That's 98% of the age of the universe. And yet, the galaxy itself is now over 32 billion light-years away, thanks to cosmic expansion. Light got here just in time to tell us what was, but not where it is. Even light loses the race. It doesn't stop there. Go smaller. Consider black holes. If you fall past a black hole's event horizon, not even light can escape. The gravity well is so deep, so steep, that the escape velocity exceeds 299,792 kilometers per second. Light doesn't slow. It simply cannot leave. It's trapped, doomed to spiral inward for eternity. That means there are places, real places, in the universe where light is useless, where it becomes a prisoner, and where no information can ever escape. Not because it's too slow in general, but because it's not fast enough to defeat gravity. On cosmic scales, time and light are inseparable. If you can't reach something in light speed terms, you can't reach it. Period. And what light shows you is never now. It's always then. Light is a history teacher, not a navigator. This has horrifying implications for exploration, for communication, for even understanding what's real. If you received a signal from a planet 100 light years away, an alien message, a cry for help, or a simple broadcast, you'd be hearing something that happened a century ago. By the time we respond, 2 centuries will have passed. Civilizations could rise and fall in that interval. The senders might be extinct. The message, meaningless. And that's if we're lucky. There are galaxies that are already unreachable. Not because they're too far, but because the rate of cosmic expansion has pushed them beyond the cosmological horizon. Light from those regions will never reach us. Not in a trillion years, not ever. They are effectively erased from our universe, beyond causality. This isn't a distant future. This is happening now. Every second, more galaxies are crossing that threshold. More regions of the universe are moving beyond communication range. And once they cross, they're gone. Not invisible. Non-interactable. We will never know their fate, never see what they become. We're watching them drift into permanent silence. That's what the speed of light does to us. It reveals the scale of our entrapment. Because in human terms, 299,792 kilometers per second is blinding, explosive, instant. But in cosmic terms, it's sluggish, underpowered, a crawl through an infinite wilderness. You could fire a beam of light now, in a straight line, and it would take over 100,000 years just to cross our own galaxy, the Milky Way. One galaxy, one disk of stars. The local group of galaxies? You're looking at millions of years. The Laniakea supercluster? Our larger cosmic home? Hundreds of millions. And then there's the observable universe, a sphere roughly 93 billion light-years across. Light could never reach the edge, not in 100 lifetimes, not ever, because the farther it travels, the more the universe expands ahead of it. It's like running on a treadmill where the track moves faster than your feet. No matter how fast you go, the destination pulls away. So yes, light is fast. But in the face of infinite space and ever-expanding time, it's not enough. It never was. And that should disturb you, because if light can't keep up, if the fastest thing in the universe can't reach where it needs to go, then what chance do we have? Our ships? Slower than snails in comparison. Our signals? Outdated before they arrive. Even our thoughts, constrained by this limit, can't escape their own delay. We are stranded in pockets of time, locked into the past, living in a reality where the present is always out of reach. And the farther we look, the older everything becomes. Because light, for all its speed, is too slow for the universe it tries to illuminate. Let's suppose right now that a signal arrives. It's unmistakably artificial, structured pulses, modulated frequencies, maybe even language, not noise, not a natural source. Something built, something sent. We trace its origin and discover that it comes from a star system 100 light-years away. Headlines explode. We are not alone. But behind the celebration, beneath the surface-level awe, an unsettling reality begins to take shape. The signal we just received? It was sent a century ago. 100 years of silence. 100 years of uncertainty. 100 years in which anything, everything, could have happened. That star system could be dead. The senders could be extinct. Their civilization might have collapsed, evolved, transcended, or vaporized. The world that transmitted the signal might no longer even exist. And whatever message we just heard, it was never intended for us. It was never meant as a conversation. It was a ghost. A voice from the past, screaming into the void, hoping someone, anyone, was out there. And now, so that we've heard it, we have to face the brutal consequence of the cosmos. There is no real-time communication across light years. Every message is a delay. Every reply is an echo. And every attempt at dialogue is a monologue stretched across generations. If we responded today, right now, at the speed of light, our reply would take another 100 years to get back. That's 200 years round trip. The people who sent the original message would be long gone. The civilization that built the transmitter might have no memory of it. Or worse, they might be listening, waiting, hoping, and dying before the reply ever reaches them. Communication with extraterrestrial intelligence is not like sending an email. It's not even like mailing a letter. It's like launching a bottle into an ocean that spans centuries. That's what light years away really means in communication terms. Not just distance, but time, delay, isolation, misalignment. By the time we speak, the conversation is already history. Now scale it up. What if the signal is from 500 light years away? Or 1,000? That means we're looking at signals sent during the height of the Renaissance, or the fall of the Roman Empire. Civilizations that existed before modern physics, before electricity, before telescopes. Imagine receiving a message today that was sent when humanity still believed Earth was the center of the universe. That's the gap we're talking about, except now it's in reverse. We're the ones behind. We're the ones just now receiving signals from beings who may have already moved on or vanished entirely. We often talk about SETI, the search for extraterrestrial intelligence, as a hopeful endeavor. We listen for signs, we scan radio bands, we build massive arrays and monitor narrow frequency ranges for deliberate transmission. But what we don't often say, what we don't like to admit, is that any message we detect is, by definition, a relic. We're not discovering alien life, we're unearthing it. Think about the implications. A signal from just 50 light years away, if aimed at us deliberately, had to be sent before the human genome was fully mapped, before smartphones, before GPS. Our entire technological era would have happened after they sent the message. Imagine what they've done since, or imagine what they've lost. The odds that two civilizations exist, develop, and achieve radio technology at the exact same cosmic moment are infinitesimal. The window for detectability, when both are listening and transmitting, is vanishingly small. This is called the synchronicity problem, and it's devastating. Maybe intelligent life is common, maybe it's everywhere. But if everyone's rise and fall happens at staggered intervals across billions of years and billions of stars, then the universe could be filled with intelligent life, and we'd still never make contact. We wouldn't know until it was too late. Until all we had were artifacts of light, traveling at maximum speed, telling stories of civilizations long dead. Even worse, there's no way to know if they ever heard us, because for them, we're ancient history too. Let's flip the scenario. Let's say humanity sends out a message today, aimed at a potentially habitable world 200 light years away. We build a high-power radio array. We encode information about biology, language, math. We beam it through space, hoping to make first contact. But if they receive it, it'll be 2225. And if they choose to reply, we won't hear back until 2325. That's 10 generations of waiting. That's systems collapsing. That's entire cultures transforming. That's wars, climate change, maybe even extinction. The people who launched the message will be dust. The civilization that crafted it might be unrecognizable or erased. Interstellar messaging isn't a conversation. It's archaeology in reverse. It's sending artifacts forward in time and hoping someone, someday, finds them. This isn't speculative. This is physics, the laws of causality, the sealing of reality itself. Because light, as fast as it is still finite, still bounded by the very structure of space-time. And that structure guarantees one thing: you can't cheat the delay. No wormhole, no warp drive, no quantum entanglement bypasses the fact that information cannot travel faster than light. And for any message that has to cross light years of space, the gap is unbridgeable in any human-relevant sense. That means alien contact, if it ever happens, won't feel like a breakthrough. It will feel like exhumation, like opening a time capsule from a civilization already consumed by entropy. This leads to a darker possibility. What if all intelligent life eventually realizes this? What if they try to send messages, wait centuries, and conclude, wrongly, that they're alone? What if the universe isn't quiet, but just too slow? What if civilizations all go through the same arc? Evolve, reach out, wait for a reply, grow disillusioned, and collapse, long before a reply could ever arrive? Then we're not isolated because life is rare. We're isolated because communication is impossible. Because across cosmic distances, even light becomes silence. And the moment we detect an alien signal, we'll finally understand what it really is. Not an invitation. Not a greeting. But a goodbye sent long before we were ever ready to listen. Let's say, for a moment, that we don't wait for alien signals. That we decide to make the first move. Not by sending a message, but by physically going. By sending a spacecraft, not to a planet in our solar system, but beyond it. To another star. 1 light year away. Just one. That single decision, just that ambition, exposes the cold, brutal economics of deep space. Because moving anything, anyone, even a gram of mass across a single light year isn't just difficult. It's nearly impossible with our current understanding of energy. And the numbers are staggering. First, let's define the challenge. A light year is roughly 9.46 trillion kilometers. To traverse that distance in any reasonable amount of time, say under a century, you need to move very, very fast. A decent benchmark? 10% the speed of light. That's 29,979 kilometers per second. For reference, the fastest human-made object, the Parker Solar Probe, clocks in at about 200 kilometers per second near the Sun. We're talking about a 150 times increase, minimum. Now, calculate what it takes to accelerate even a small spacecraft to that velocity. Take a 1-ton payload, barely enough for instruments, shielding, a communications array, and power systems. No crew, no life support, no redundancy, just a robot probe. To accelerate this 1,000 kilogram object to 10% the speed of light, you'd need E equals 1/2 mv squared, which gives you E equals 0.5 times 1,000 kilograms, times open parenthesis 29,979,000 meters per second. Close parenthesis squared equals 8.49 times 10 to the 20 joules. That's 449 quintillion joules. To put that into perspective, that's more energy than the entire planet Earth consumes in a year. In fact, global energy consumption in 2022 was about 6 times 10 to the 20 joules. So you'd need nearly 75% of all global energy output for a full year just to send a toaster-sized payload to 10% of light speed, and that's ignoring drag, inefficiency, and fuel mass. Now imagine sending a crewed ship, a life-supporting vessel with shielding, food, water, radiation protection, and a propulsion system that can keep humans alive for decades. You'd need thousands of tons of mass and exponentially more energy. Try doing that with chemical rockets, the same basic technology we've used since the 1960s. Their exhaust velocities are pathetic by comparison. A SpaceX Falcon Heavy burns through almost all of its fuel just to escape Earth's gravity. To reach 1 light year? Not possible. The amount of fuel required would exceed the mass of all matter in the solar system. Literally. So we move to ion propulsion, high-efficiency, low-thrust engines. NASA's Deep Space One used one to travel to an asteroid, and Dawn used it to orbit Ceres. They sip fuel instead of guzzling it, but they produce millinewtons of thrust. Your microwave door closing hits harder. Getting to even a small fraction of light speed with an ion drive would take centuries, assuming it doesn't run out of fuel or electronics, don't degrade in the radiation-rich vacuum of space. Then there's nuclear propulsion. Concepts like Project Orion proposed using controlled nuclear explosions. Yes, actual bombs detonated behind a spacecraft to generate thrust. Theoretically, it could get us to 10% of light speed. But the trade-offs are catastrophic. Massive radiation exposure, extreme engineering challenges, and the small problem of detonating hundreds of nuclear bombs in succession in space, an act no treaty allows. Another idea, fusion propulsion, like the hypothetical Daedalus or Icarus missions. These involve miniaturized fusion reactors providing sustained thrust over decades. Sounds promising, except we haven't built a single working fusion reactor that produces net energy on Earth, let alone one compact and stable enough to launch into space. And even if we did, the fuel, helium-3, is almost non-existent on Earth. We'd have to mine it from the moon or gas giants first, just to fuel the first mission. Then there's antimatter. 1 gram of antimatter reacting with matter yields 90 trillion joules of energy, enough to power the US for a day. Great, except we can barely produce nanograms of antimatter per year, at astronomical cost. Storing it is another nightmare. Antimatter annihilates on contact with matter. You'd need a magnetic trap operating flawlessly in deep space with zero containment failure allowed. A single micro leak? Your ship explodes with the force of a tactical nuke. Even the most efficient theoretical drives, like the Bussard ramjet, which collects interstellar hydrogen to use as fusion fuel as it moves, fall apart under real physics. Space is too empty. The drag from the scoop exceeds the thrust you could generate, and that's assuming perfect fusion reactions and perfect engine efficiency, which don't exist. So we move further into science fiction. Laser sails. The Breakthrough Starshot initiative proposes firing powerful ground-based lasers at small, gram-scale spacecraft equipped with light sails. In theory, these tiny craft could reach 20% the speed of light. But even then, there are enormous obstacles. The spacecraft must survive acceleration forces of thousands of Gs. It can carry no shielding, no instruments, no camera, and no communication array that would survive deceleration. A single speck of dust at 0.2 C is like a bullet traveling at Mach 60,000. And worst of all, you can't slow down. There's no onboard fuel. Once it's launched, it's a flyby mission. No orbit, no stop, no return. In every case, the reality is the same. Distance is the enemy, and energy is the cost. Even moving a single human being a fraction of a light year would require energy budgets that eclipse anything civilization has ever achieved. A trip to Proxima Centauri, 4.24 light-years away, would take thousands of years with chemical propulsion, centuries with ion or nuclear propulsion, and still require obscene energy expenditures with anything faster. And time isn't your only problem. Radiation becomes lethal at relativistic speeds. The faster you move, the more interstellar hydrogen atoms slam into your spacecraft like high-energy bullets. You'd need shielding meters thick, adding mass, which increases energy costs, which requires more shielding, and so on. Heat buildup becomes a concern. At high speeds, the background microwave radiation of the universe itself blue shifts into dangerous X-rays. Your ship slowly cooks, not from internal systems, but from the universe itself. Even assuming perfect technology and unlimited energy, there's still the problem of course correction. Traveling a light year means tracking position with millimeter precision over trillions of kilometers. Any deviation compounds. Miss by a fraction of a degree, and you overshoot your target by billions of kilometers. And all this just to move one object 1 light year. That's not even travel. That's just motion. That's just existing at a distance that, by every engineering standard we have, is functionally unreachable. It becomes clear why all interstellar travel, serious, non-fictional proposals, focus not on humans, but probes. Cheap, lightweight, disposable. Send thousands, let a few survive, hope for data, and wait. But even those require gigawatt-scale launch systems, coordinated laser arrays, cooling systems, and decades, centuries of lead time to move a chip with a camera. The simple truth is that 1 light year is not a journey. It's a wall built out of vacuum, time, and physics. And while we can measure it in kilometers or joules or years, what we're really measuring is our powerlessness. Light may cross that distance in 12 months. We, on the other hand, might never do it at all. If the math doesn't break your hopes for interstellar travel, Hollywood will. Because for decades, science fiction has been quietly, and often spectacularly, lying to you. You've seen it all. Warp drives stretching stars into streaks, ships vanishing into hyperspace, wormholes opening like doorways in reality, and cryo-sleep chambers gently waking up crews after crossing galaxies like they just took a nap. But these aren't predictions, they're illusions. Elegant fiction draped in just enough science to feel plausible. But the truth? The real physics behind these ideas doesn't just cast doubt, it dismantles them. Let's start with the most famous deception: warp drives. Thanks to Star Trek, the term warp has entered the public vocabulary as a stand-in for faster-than-light travel. You hear it, and you don't flinch. The ship goes to warp. It bends space. It outruns light. No big deal. But the moment you take that idea into actual physics, the cracks become impossible to ignore. The concept behind the warp drive comes from a 1994 paper by physicist Miguel Alcubierre. He proposed that you could compress space in front of a ship and expand it behind, effectively riding a wave of space-time. The ship itself wouldn't be moving through space. It would be moved by space. Clever, legal. Not faster than light travel in the traditional sense, just a manipulation of the fabric of the universe itself. But here's what the public rarely hears. To make that warp bubble work, the math requires exotic matter with negative energy density. Not theoretical, as in rare. Theoretical, as in may not exist. The energy cost to generate such a bubble was initially calculated as the mass energy equivalent of Jupiter. Later refinements have reduced that to about the energy contained in several suns. So we're now only a few entire stellar outputs away from making it work. That's before you deal with the fact that the front edge of a warp bubble traps all incoming radiation, accumulating it into a deadly beam. When the bubble collapses, that energy is released forward at once, possibly vaporizing whatever you were trying to reach. It's called the termination shock, and in simple terms, a warp drive may function like a relativistic battering ram. Now, shift to wormholes, Einstein-Rosen bridges, shortcuts through space-time. Fold a piece of paper, stab it with a pencil, and voila, travel from A to B without crossing the distance between. Instantaneous travel, two-way communication, the holy grail of cosmic transport. But that's a classroom metaphor, not a machine. To build a wormhole stable enough for travel, you'd again need exotic matter to prevent it from collapsing. And even if you had that, you'd need to construct it, meaning you'd have to reach both ends first. So no, you can't use a wormhole to explore a place you've never been. Worse, the moment you attempt to send mass through it, gravitational forces threaten to destabilize the throat. It collapses, cutting the connection. It's like trying to use a doorway that vanishes the moment you step through. So even if wormholes exist, they're more like portals you can't walk through. Cosmic illusions, cryogenic sleep, the most grounded idea in science fiction? Let's dissect that too. The trope is everywhere, from Alien to Interstellar to 2001, A Space Odyssey. Humans climb into sleek pods, enter suspended animation, and emerge decades or centuries later, refreshed and unharmed. But in reality, putting a human into long-term stasis is not a solved problem. Not even close. Yes, some animals enter torpor. Yes, frogs can survive being frozen. But humans, every cell in your body contains water. Freeze it, and ice crystals form. Those crystals shred membranes. Organs rupture at the microscopic level. Even flash freezing doesn't prevent cellular damage. Cryoprotectants, chemicals that prevent ice formation, exist, but they're toxic in high doses. You can vitrify small biological samples, embryos, tissues, but full body vitrification of a human? Not without killing them first. And even if you could freeze someone safely, there's the problem of reversal. Warming a body evenly without causing thermal shock or tissue damage is absurdly difficult. To date, no mammal has been cryopreserved and revived. None. Not even a mouse. Hibernation is another avenue. NASA is funding research into torpor for astronauts, lowering body temperature and metabolic rate to reduce life support needs. But we're talking about weeks, maybe months, not centuries, and not across light years. Then there's the forgotten enemy in all of this: time. Even if you solve energy, even if you build a warp engine or invent stasis, time remains unforgiving. In science fiction, ships arrive at other star systems in hours or days. But real-world physics gives you years, decades, lifetimes. Time to accumulate radiation exposure, hardware fatigue, navigational error. Time for your mission to become irrelevant. Think of the generation ship model. Launching a self-sustaining ecosystem with thousands of people to live, breed, and die en route to another star. It sounds poetic until you calculate failure modes, genetic drift, cultural collapse, mechanical breakdowns, even tiny imbalances, air composition, food supply, microbial mutation, become existential threats over centuries. In a sealed environment, there's no margin for error, no help, no return. Sci-fi doesn't show you that. It gives you clean bridges, blinking consoles, dramatic countdowns. But not entropy, not boredom, not death by engineering failure. It sanitizes the horror of scale. The psychological manipulation is subtle but constant. Films compress time to maintain narrative flow. One jump and you're in another system. One device and you're in another galaxy. Viewers absorb this as normal. They internalize the idea that interstellar travel is simply an engineering problem. Difficult, but solvable. That's the real danger. Not that science fiction is wrong, but that it teaches the wrong expectations. That it leads audiences, and even policymakers, to believe that space is conquerable within a human lifetime. That all we need is better engines, bigger rockets, smarter designs. But the enemy isn't just technical, it's physical. It's the speed of light, the energy cost of momentum, the sheer size of the void. And fiction, for all its creativity, doesn't fight fair. It bypasses physics for plot. Ask yourself, in Star Wars, how do ships go from system to system? Hyperspace. How does it work? It doesn't matter. It's a term that exists only to skip the problem. In Stargate, you step through a ring and end up in another galaxy. In Mass Effect, you use Element Zero. In Doctor Who, the TARDIS spins through the time vortex. These are narrative devices, not scientific theories. And the danger is that they blur the line. They make impossibility look routine. They make travel to Alpha Centauri seem no harder than a road trip. But in reality, we're still struggling to send a crewed mission to Mars. That's 0.000015 light years away. We are not remotely close to crossing a single light year. Not physically, not biologically, not energetically. Every serious proposal collapses under the weight of energy costs, engineering limits, biological constraints, and the cold speed limit of the universe. So when fiction tells you space is waiting, when it shows you stars just a jump away, it's not showing you the future, it's showing you an illusion, one that we may never live long enough to see broken. When we look up at the night sky, we think we're seeing the present. But we're not. We're seeing ancient history stretched across the void, broadcast in photons that took eons to arrive. And the deeper we look, the farther we reach, the more disturbing the truth becomes. We are not observers of the universe as it is. We are archaeologists of light, sifting through temporal wreckage, trapped in a one-way view of a cosmos that may no longer exist. Because in cosmic terms, distance is time. Every light year between us and an object equals 1 year of travel time for the photons it emits. So when we see a galaxy that's 10 billion light years away, we're not seeing it as it is today. We're seeing it as it was 10 billion years ago, back when Earth was a molten planet, before the solar system formed, before even the Milky Way had completed a single galactic rotation. And here's the twist. That galaxy may no longer be there. It may have merged with another. It may have burned out. It may have collapsed into a black hole. Or it may have simply aged beyond recognition. But we'll never know. Because the light telling us what happened next won't reach us for another 10 billion years. That's not speculation. That's how light works. That's how causality is enforced in this universe. The speed of light isn't just a velocity, it's a limit, baked into the geometry of space-time, defining the edge of what's knowable, what's observable, what's real. And that raises a disturbing question. If all we can see is the past, then do we ever see the present? The answer is no. Not in cosmic terms, not even close. Even the moon, just 384,000 kilometers away, is seen as it was 1.3 seconds ago. The sun? 8.3 minutes in the past. Every star in the sky is a memory, a delay, a signal that departed long before we knew how to read it. This isn't a metaphor. It's not poetic. It's not philosophical. It's physics. There is no cosmic now. No universal present. The idea that everything is unfolding simultaneously is an illusion created by human-scale perception. Einstein shattered that notion with special relativity. Time and space are not fixed. They are relative, shaped by velocity, gravity, and the observer's frame of reference. So, what does it mean to see something as it is? In a relativistic universe, that's the wrong question. The better question is, when are we seeing it? And the answer is always, some time ago. For objects millions or billions of light years away, it's not just a delay, it's a cosmic chasm. And the implications go further. If we receive light from a galaxy 13 billion light years away, we're seeing it from a time when the universe was just 500 million years old. We're watching the universe itself form stars for the first time. We're seeing the early frames of a film that has already played out, but whose later scenes remain hidden behind a temporal firewall. It's as if you're reading a book where every page takes billions of years to turn, and you can never skip ahead. And here's where the paradox emerges. We often talk about time travel as a hypothetical, a fantasy of science fiction. But the universe is already doing it. Not by moving objects through time, but by embedding time in space. Every direction you look is a look backward. Every telescope is a time machine. And that creates a chilling reality. We may be looking at things that have already vanished. A supernova explosion 150,000 light years away may have dimmed into nothing centuries ago. But the light of its death is just now reaching us. To us, it's alive. To the universe, it's history. Worse, the farther out we look, the more likely it is that what we're observing is gone. Galaxies beyond a certain distance, known as the cosmic event horizon, are receding faster than the speed of light due to the expansion of the universe. That's not breaking physics, it's space-time itself stretching. And it means that any light they emit today will never reach us. Not now, not ever. So not only are we seeing the past, we are trapped in it, permanently. There's a name for this boundary, the particle horizon. It defines the edge of the observable universe. Right now, that radius is about 46.5 billion light years, even though the universe is only 13.8 billion years old. How? Because space has been expanding while light has been traveling. Space stretches, but light just keeps moving at the same speed. And that stretch creates a terrifying divide. What's beyond the horizon is forever hidden. Not because it doesn't exist, but because we're too late. Even if we had infinite sensitivity, if we could detect single photons across infinite time, we'd never see beyond that wall. Not because it's dark, but because the light is still on its way, and always will be. So when you gaze at the most distant objects in the cosmos, remember, you're not seeing their future. You're not even seeing their present. You're seeing echoes, fossils, shadows of processes that ended before our planet cooled, light from galaxies that have since moved out of reach and whose next moment we will never witness. And the deeper tragedy? We are subject to the same fate. The light we emit, our radio signals, our telescopic glows, our planetary reflections, is also on its way outward. 1,000,000 years from now, a distant civilization might detect the signal from our first artificial satellite. But by the time they try to respond, we may be long gone, or transformed, or unreachable. They will be looking into our past and asking the same question: are they still there? But they'll never know, just like we never will. In a universe ruled by the speed of light, time isn't something we move through. It's something we're bound to. Every look at the stars is a look backward. Every photon is a messenger from a moment we'll never return to. Every observation is a confession. We are always late, and we will never catch up. So if we're always late, always catching glimpses of the past frozen in transit, then the next logical question is, what past? When we look out across those trillions of kilometers, what moments in Earth's own history align with the light we're just now receiving? Because each distant cosmic object, each star, quasar, nebula, or galaxy is not just a marker in space. It's a timestamp, a literal record of time encoded in photons arriving now but launched at some specific point in Earth's long, violent, and improbable journey through history. And once you start decoding those timestamps, the comparisons become unsettling. Take Messier 87, a giant elliptical galaxy in the Virgo cluster, located about 53 million light-years from Earth. That's the galaxy that houses the now iconic supermassive black hole imaged by the Event Horizon Telescope in 2019. The image we saw, the donut of death with its glowing ring of accreting plasma, is not how M87 looks today. It's how it looked 53 million years ago. Back then, on Earth, primates were just beginning to appear. The dinosaurs were gone, wiped out by the Chicxulub impact a few million years earlier, and mammals were rising to fill the vacuum. Australopithecus, Homo sapiens, even the idea of intelligence were still tens of millions of years in the future. The black hole you saw on your newsfeed was older than our evolutionary lineage. Now, jump to NGC 4993, a galaxy 130 million light-years away. In 2017, gravitational wave detectors and telescopes around the world picked up a kilonova there, a collision between two neutron stars spewing gold and platinum into space, warping space-time and unleashing gamma rays. This was the first time humanity directly witnessed both light and gravitational waves from the same cosmic event. But while we celebrated the discovery, something darker was in the background. That explosion didn't just happen. It happened 130 million years ago. At that time, dinosaurs still walked the Earth. The late Cretaceous was in full swing. Tyrannosaurs hunted in what is now North America. Flowering plants were diversifying. Mammals were tiny, rodent-like survivors. The signal of that ancient explosion has been crossing the void ever since. While continents drifted, species evolved, and a primate ancestor climbed into the trees and began a long, slow march toward consciousness. And then there's the Sombrero Galaxy, M104, lying around 31 million light-years away. When the light we now see from its bright central bulge began its journey, Earth was experiencing the Oligocene epoch. Early horses the size of house cats grazed in open grasslands. Massive flightless birds stalked prey across plains. The Himalayas were still rising, and Antarctica had just begun to freeze over. That light traveled for 31 million years, through intergalactic voids, past clouds of dust and magnetic fields, until it hit our detectors. And during that time, every single human ancestor lived, evolved, and died without ever knowing such a galaxy existed. Let's go even further. The Andromeda Galaxy, our closest large galactic neighbor, is about 2.5 million light-years away. That's practically next door on a cosmic scale. Yet the light we see from it tonight, its cloudy swirl just visible in a dark sky, departed when early humans first appeared. That's right, 2.5 million years ago marks the appearance of Homo habilis, one of the first species in our genus. These tool-using hominins hadn't yet mastered fire. They had no language, no culture, no concept of stars. But while they chipped stones in the African Rift Valley, photons were already hurtling toward Earth, photons that would outlive ice ages, empires, and entire civilizations before reaching our retinas tonight. That means every time you look at Andromeda, you're seeing the universe as it was when the first humans walked the planet. Now, stretch farther. GNZ 11, one of the most distant galaxies ever observed, lies 13.4 billion light-years away. When its faint red-shifted photons left that primordial system, the universe itself was just 400 million years old. Earth didn't exist. The Sun didn't exist. The Milky Way was still forming. There was nothing here. No oceans, no continents, no atmosphere. Just interstellar dust and the molecular ingredients that would one day coalesce into a planetary system. That light crossed empty space before our solar system had even formed, before time, as we understand it, had meaning in this corner of the cosmos. And it's still coming. Not all these examples are galaxies. Some are stars in our own galaxy, and even they can stretch our timeline. Consider Betelgeuse, the red supergiant in Orion. It's about 642 light-years away. That's relatively close. But it means any change in Betelgeuse, like a potential supernova, has already happened. If it exploded 641 years ago, we'll find out this year. What was happening on Earth when the light we see tonight left Betelgeuse? The year was 1383. The 100 Years' War raged in Europe. The Ming dynasty ruled China. The printing press had not been invented. Galileo was still a century and a half from birth. And yet, that ancient starlight has been crossing space all this time, slipping past stars and nebulae, until it found your eye or your telescope, bringing with it a delayed snapshot of cosmic truth. The same applies to supernovae in other galaxies. The famous SN 1987A in the Large Magellanic Cloud exploded roughly 168,000 years ago, but its light reached Earth in 1987. That means it died when Neanderthals still roamed Europe, long before recorded history, long before writing, agriculture, or architecture. The sky we see is not the sky as it is. It's a timeline of everything that was. And it's not just light that tells these stories. Every photon from these distant objects is redshifted, stretched by the expansion of space, encoding the age of the universe at the moment of departure. Our instruments don't just measure light, they measure time travel. This is what telescopes do. They're not just lenses, they're time machines. They pierce the veil of now and let us see how the universe unfolded, frame by frame, photon by photon, across an unimaginable scale of time. Each cosmic object is a fossilized moment of universal history, captured not in rock but in light. And Earth's own timeline is the eerie backdrop. When you look at a star, you're seeing what Earth was doing when that light began its journey. When you see a galaxy, you're seeing a cosmic event cross paths with a terrestrial one. The formation of stars mirrored against the rise of mammals. The explosion of a neutron star set against the extinction of dinosaurs. The birth of the universe itself observed by creatures whose ancestors hadn't even existed when that light began moving. The deeper you look, the farther back you go, not just into the cosmos, but into ourselves. We are not just in the universe, we are locked to its timeline, observing the past, unable to break through to the present, and forever watching history unfold in the sky, even as our own unfolds below it. Let's say everything else changes. Let's say we solve propulsion, crack fusion drives or antimatter engines. Let's say we master cryonics or engineer long-term hibernation. Let's even grant ourselves a breakthrough in space-time manipulation. All of it. Even then, we remain shackled to one devastating truth. Light years don't care. They are not walls you can tear down. They are not puzzles to solve. They are reminders, cold, unyielding, that space isn't just empty, it's immense. And there's no guarantee that any amount of intelligence, persistence, or innovation will ever be enough to overcome that scale. This is the light-year barrier, and it's not just a scientific challenge. It's a psychological wound. Because once you understand what a light year truly is, once you internalize what it takes to even reach the nearest star, you come face to face with the possibility that humanity might be trapped. Not temporarily, not until the next breakthrough, but permanently. Alpha Centauri, our closest stellar neighbor, is 4.37 light-years away. With our current best propulsion systems, it would take tens of thousands of years to get there. Even if we accelerated a spacecraft to 0.1 times the speed of light, a level of engineering we are nowhere near achieving, it would still take over 40 years to arrive. One direction. And that's just for data. Not for people. Not for return trips. Not for civilization. When you extrapolate that to real exploration, to spreading out, colonizing, moving among the stars, it becomes clear how unreachable the rest of the galaxy is. Let alone other galaxies, let alone the universe. It is not a matter of building a better ship. It is a matter of confronting a scale so vast, so detached from our biology, that it annihilates optimism. And this understanding has consequences. Because for the past century, humanity has conditioned itself to believe in progress without limits. We broke the sound barrier. We put people on the moon. We decoded the genome. We built machines that learn, and probes that drift beyond Pluto, and telescopes that peer into the origin of time itself. Each breakthrough reinforced the same story, that with enough effort, no frontier is beyond our reach. But space disagrees. Space, true space, the interstellar gulfs between stars, is not impressed by ingenuity. It doesn't care how clever we are. It doesn't care that we want to visit. It doesn't care that we dream. It's just there, and it's enormous. And the emotional fallout of realizing that is something we're only just beginning to reckon with. Because when we accept that the stars are out of reach, we also begin to question our place, our meaning, our future. What is the long-term trajectory of a civilization that can't expand? What happens to exploration, to ambition, to identity when we hit the wall? For centuries, expansion has been a core feature of human history. Cross an ocean, conquer a mountain, settle a new land. It's not just geography, it's psychology. Growth has always been the model. More land, more resources, more access, more reach. But light years laugh at that logic. They impose a hard boundary, one that shrinks even our wildest ambitions into a tiny, irrelevant speck. The entire solar system? A grain of sand in a galactic desert. The galaxy itself? One among hundreds of billions, each increasingly unreachable with every passing second. That shrinking of scope seeps into everything. What becomes of science when the ultimate questions lie forever outside the range of testing? What becomes of meaning when you know you'll never stand beneath another star? It's not just a technological problem, it's a spiritual one. It forces us to abandon the myth that the universe is ours to explore. It isn't. It's not even ours to glimpse. Most of it is too far, too fast, too gone. We are observers, that's all. And while science fiction has long comforted us with dreams of warp drives and galactic federations, those are fictions for a reason. They paper over the silence, the isolation, the vast, unbridgeable gap. We built stories to avoid staring into the void, but physics doesn't care about stories. And here's the deeper truth. If the light-year barrier is permanent, if we can't punch through it, hack around it, or tunnel past it, then this is all we'll ever have. This solar system, this one sun, these few rocky worlds. And that realization fractures something fundamental. It breaks the illusion that we are cosmic explorers on the brink of a second age of discovery. It reveals us instead as cosmic castaways, marooned on a planetary island, watching the stars but never touching them. For a species wired to explore, that is a psychological prison. You begin to see a different kind of future, one not of outward expansion, but inward reckoning. A future where we are forced to focus not on colonizing the galaxy, but on surviving inside our sealed bubble of influence. A future where we build inward instead of outward, crafting megastructures, optimizing habitats, managing entropy. Not because it's efficient, but because it's necessary. The stars will always be there, brilliant, distant, silent, and we will always be here, looking up, wanting, but not reaching. And no amount of dreaming changes that. Because at the end of all our ambition, all our calculation, all our effort, the light year stands unmoved, unbroken, untouched. A constant reminder that in the story of the universe, humanity may always be a footnote. Not because we lacked imagination, but because the universe was never designed to be visited, only seen from far away in silence. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.